Hello and welcome to this special series of System Verilog Assertion. In the last video of this series, we had a discussion about the contents, what we are going to discuss as a part of this series. Already we discussed a very high level introduction to the System Verilog Assertion. In that, I already covered what are assertions, need of assertion, why assertions are needed, who will write the assertion, whether it is a responsibility of a design engineer or a verification engineer. Then we saw advantages of assertions, some limitations of assertions, and the System Verilog Assertion SVA in System Verilog Event Scheduler. Okay, then I told you in the last video itself that these are the books that I am referring. A Practical Guide for System Verilog Assertion by Shrikant Vijay Raghavan. Assertion Based Design 2nd edition by Harry Foster, and System Verilog Assertion and Functional Coverage by Ashok. You can also refer these books for more understanding and more detailed analysis. Okay, now let me explain you what the topics we are going to cover as a part of today's video. So in today's video, I will explain you some built-in system functions with respect to SVA System Verilog Assertion. In this built-in system function, we will discuss $rows, $fill, $stable, $change, and $pass, and etc. There are many built-in system functions. We will discuss those system function generally we are using in our verification environment. Those are very famous or popular. We are going to discuss as a part of this video. Okay, and we'll try to understand with the help of sample code and with the help of the sample waveform for each built-in system function. Before moving to on system functions and waveform, let me explain you what built-in system functions are all about. So System Verilog Assertion SVA has built-in age expression that allow the user to monitor the transition of signal value from one clock cycle to the next. And this allows checking for the age sensitivity of signals. I hope you are aware about age sensitivity, passage and neg age, right? And some of the useful built-in functions are $rows, $fill, $stable, $change, okay, $pass, and etc. We are going to discuss few of them as a part of today's video. Before that, let me explain you, as we are considering the waveform for each built-in function, we are understanding with the help of sample waveform and sample code. Let me tell you how we can analyze the waveform. So these are the points you should remember while we are discussing the waveform. Okay. So this blue square is there in the waveform, as you can see. It notifies the assertion is a start. Green triangle is there, which will notify, as you can see over here, green triangle is there, which will notify the assertion pass, and red triangle shows the assertion fails. Okay, and in concurrent assertions, The concurrent assertions use the values that are sampled in the pre-pawned region of the event scheduler. Already we had a discussion about this point in the last week. This means just before the passage of the clock, we have to take the values of the value. And these are the three main reasons of the event scheduler in which assertion is associated. Pre-pawned region, where sampling of the assertions are happening. Observed region, where evaluation of the concurrent assertion will happen. And reactive region. At this reactive region, we'll find the pass and fail messages from the assertion. If we are writing the action block, which is optional one, that action block response you will find in the reactive region. Okay, so this POR, pre-pawned, observed, reactive region are associated with the system Verilog. Let me explain you each system function one by one with the help of sample code and sample waveform. Okay, so as you can see over here, the $rows system function. This system function returns true or 1 if the LSB list significant bit of signal or expression changed to 1. So the signal is changed to 1. This system function will return 1 or 2. And as you can see over here, this is what the sample code for this $rows. So property P1 and property at the rate passage of the clock, meaning at every passage of the clock, we are checking the value of this variable A. If it is changed to 1, we'll find the assertion will pass, else the assertion will be fail, and then we are asserting that property. Okay, this is what the sample code, not a complete code. I will show you the complete code. Okay, let's try to understand this with the help of this waveform. Okay, so as you can see over here, this is the clock. Okay, and this is the value of A. Okay. Let me explain you with the help of waveform. Let's consider this passage of the clock. Okay, let me take a pen. Okay, so this is what the passage of the clock. This is next passage of the clock. Let me mark the passage of the clock so that it become easy for us to understand the waveform. So let's consider this passage of the clock, because we are writing at every passage of the clock $rows of A. Okay, so at this passage of the clock, you will find the value of A is 1 over here, right? Because the values in concurrent assertion is sampled in the pre-pawned region, meaning just before the passage of the clock. Okay. So value of A is 1 here, and the value is changing from this 0 to 1 here, right? Meaning we are able to see the signal is changed to 1, right? Hence the assertion is passing over here. You will find this green triangle. Okay. Let's try to understand in another clock cycle. As you can see over here, the value of A here at this clock edge, at this passage of clock, value of A is 1. So it is not changing from 0 to 1. Hence the assertion is failing over here. In the next clock edge also value is 1. It is not becoming, or it is not changed to 1 from 0 unknown or Z. It is just 1, because here it is 1, in previous cycle it was 1. Hence the assertion is failing over here. Similarly, at this passage of the clock, at this passage of the clock, and at this passage of the clock, you will find assertion is failing over. Now here also, if you analyze at this passage of the clock, you'll find the value of A is 0. Okay. And in the previous clock cycle it was 1, right? So it is changing from 1 to 0. But we want it should change to 1, whether it is from 0, unknown, or Z to 1. We are not interested in 1 to 0. Okay. Hence you will find assertion is also failing over. In the next clock cycle, as you can see over here, the value of A is becoming 1 and it is changing from 0 to 1, right? It changed from 0 to 1. Hence the assertion is passing over here. So you will find that this green triangle. Okay, means assertion is passing. Okay, so I hope you have understood this and you can verify for other passage of the clock similar. Let me show you the console result. As I told you, if you are not writing the action blocks, simulator system Verilog is developed in system Verilog assertion is developed in such a way that if you are not writing any action block, pass or fail messages, simulator is expected to print the error messages whenever the assertion is failing. Okay. So as you can see over here, the red triangles are there. This is nothing but the assertion failing. Okay. And it's same if you analyze in the waveform, you'll find the error messages for that time instance, for that particular time. If you check the assertion tab in Ghost-Async, you will find that it will show the failure count and pass count. Okay. Let me explain you that also. So if you analyze the red triangle over here, if you see red triangle here, you will find if you count it, you will find it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. From here to at the last, you will find 14 are red triangles are there, meaning assertions are failing. So you'll find the failure count is 14 over here. Similarly, if you count this green triangle, you'll find there are 6 pass messages. So you can analyze that table. So this is what the $rows system function. It will check the signal is changed to 1. Okay. Let me show you the complete code for that. Okay. I will put a link of the same code in the description so that you can go through it and you can play around with this code. So this is what a very simple code I have written. Module, end module. I wrote a very simple logic. I'm defining 2 variables of bit type clock and A. I'm generating a clock at always #5 clock is equal to not of clock. And within initial begin block, I'm generating the random values for A 20 times after delay of every passage of clock. And then I'm stopping it after generating 20 values. After 10 time unit, I'm stopping the simulation or suspending the simulation. Here I'm writing a property P1 at the rate passage of the clock, $rows of A as we discussed, and just I'm asserting the property. In another initial begin block, I'm dumping the file in order to see the wave. So you can go through with this code, you can play around with this code, you will find the output something like that, but you will not find from something like this in ADAP. You will find this waveform in Ghost-Async. Okay, so I will put a link of that code in the description. You can go through it and you can play around with this code. Now let me explain you another system function, interesting $fill system function. So this system function returns true if the LSB least significant bit of the signal or expression changed to 0. Okay. Similar to $rose only, just here, if it is changed to 0, we'll find the assertion will pass. Okay, let me explain you with the help of this sample code. So here property P1, in property I'm writing a very simple code that every passage of the clock $fill in the variable E. And here I am asserting the property P. Let's try to understand with the help of the sample code. Okay, so if you analyze, these are the passage of clock. Let me mark this so that it becomes easy for us to analyze the waveform. Okay, so let's try to understand here what this $fill is all about. If you see over here, the value of A is 0, right? If you see, the value of A is 1 over here, right? At this passage of the clock, and it was 0 in the previous clock cycle. Now it is changing from 0 to 1, but we want the signal or expression change to 0, whether it is from 1 to 0 or unknown to 0 or high impedance to 0. We want to check that, right? But it is changing from 0 to 1, hence the assertion is failing over. Similarly, at this passage of the clock, you'll find the value is 1. It is not changing to 0, hence the assertion is failing here. Similarly, here at this passage of the clock, at this passage of the clock, at this passage of the clock, you will find the assertions are failing because the value of signal A is 1. But if you analyze at this passage of the clock, you will find the value of A is 0 over here in the pre-pond region, right? Now it is changing from 1 to 0, hence the assertion is passing over. You will find the green triangle over here, right? Meaning, if the signal or expression is changed to 0, we are able to see the pass in the wave. Similarly, in the next clock cycle, you will find the value is 1, meaning it is changed from 0 to 1, and the assertion is failing. If you analyze at this passage of the clock, the value is changed to 0, hence the assertion is passing over, and so on. You can analyze the waveform. So if you analyze the console result, you will find the error messages are like this. Whenever the assertions are failing, you'll find the fail or error messages over there, assertion error message. If you see the assertion tab over there, if you count the failure, red triangles over there, you'll find these are the 15s failure count and 5 are the pass counts in the waveform. So if you just count, let's say here pass, this 1, 2, 3, 4 and 5, so you will find 5 pass counts over. Okay, so this $fill basically return true or 1 if the least significant bit of the signal or expression changed to 0. Now let me explain you another interesting system function is $stable. So this $stable system function is return true or 1 if the value of signal or expression did not change in the current evaluation point and the previous evaluation point. Okay, let's try to understand with the help of a sample code in sample. Here you will find property P1 at the rate passage of the clock $stable in A. Okay, so let's try to understand with the help of this sample. If you analyze this passage of the clock, you will find the value of A is 1 over here, right? Just before passage of the clock, meaning in the pre-pond region, we have to check the value, right? We have to take the value, those are there in the pre-pond region of the event schedule, meaning just before the passage of the clock. Let me mark the passage over here so that we easily analyze the waveform. So okay, analyze, let's try to understand the waveform, the sample wave. So at this current evaluation point, the value of A is 1, and in the previous evaluation point the value is 0. Okay, so what we want, the value of signal and expression did not change in the current evaluation point and the previous evaluation point. But if you are analyzing over here, you will find in the current evaluation point it is 1, and in the previous evaluation point it was 0. Hence the assertion is failing over here. In the next clock cycle, let's try to understand. Here if you see at this passage of the clock, the value of A is 1 in the current evaluation point, and in the previous evaluation point it was 1, right? So it is not changing, meaning it is stable only. Hence the assertion is passed. Similarly here you will find the value is 1 in the current evaluation point, and it was 1 in the previous evaluation point. Hence the assertion is passing over here, and so on for all. Okay, here also assertion will pass, here also assertion will pass, here also assertion will pass, because the values are same or stable in current and previous evaluation point. Hence you will find the assertions are passing. Let's try to understand here. At this passage of the clock, the value of A is 0 here, and in the previous previous evaluation point it was 1. Hence assertion is failing over here, meaning it is changing from 1 to 0. What we want in here, the value of the variable or signal did not change in the current and previous evaluation point. Hence assertion will be pass, else assertion will be fail. So this system function will check the stable values of signal or expression in the current and previous evaluation. And if you analyze the console result, you will find the error messages whenever the assertion is failing. So assertion error messages you will find in the console. Okay, if you analyze the assertion tab, you will find the pass counts are 9 and failure counts are the 11. Okay, so let's analyze that. Okay, so if you just count the failure, red triangle, you will find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So failure counts are the 11, and pass count, if you verify here, cross check, you will find those will be 9. Okay, so this is what the system function, $pass system function. Now the next $stable system function. Now the next is $change system function. This system function returns true or 1 if the value of a signal or expression is change, okay, or change in the current evaluation point and previous evaluation point. Let's try to understand with the help of this sample code and sample wave. Okay, so here I'm writing at every passage of the clock in the property and end property $change in this variable A. Okay. If there is a change in variable A at every passage of the clock, assertion will be passed, as we are writing assert property, else assertion will be failed. Let's try to understand that with the help of this, with the help of waveform. So let me mark the passage of the clock over here, so that we'll understand it easily. Okay, so let's try to analyze the waveform. As you can see over here at this passage of the clock, the value of A is 1. Okay, and in the previous so this current evaluation point, the value of A is 1, and in the previous evaluation point the value of A is 0, meaning it is changing from 0 to 1, right? Hence the assertion is passing over here. If you analyze here of the clock, you will find the value of A is 1 in the current evaluation point, and it is 1 in the previous evaluation point, meaning it is same, not changing, and the assertion will be failed. Similarly at here, at this passage of the clock, at this passage of the clock, and till this, you will find the assertion will be failed, because the value of the signal or this variable is not changing. in the current evaluation point and the previous evaluation point. Value is stable only, hence the assertion is failing. If you analyze over here at this passage of the clock, the value of A is 0, then current evaluation point it is 0 and the previous evaluation point it is 1. As it is changing from 1 to 0, you will find assertion is passing over here. At this next passage of the clock, as you will find the value of variable A is 1, so it is changing from 0 to 1, hence the assertion is passing over here. Okay, so this is what the $change system function. If the values change in the current evaluation point and previous evaluation point, you'll find the assertion will pass over here in the wave. And these are the sample, console result. Whenever the assertion is failing, you'll find the assertion error over there. If you analyze the assertion tab, you will find 9 are the failure and 11 are the pass over here. So if you just cross check, you'll find this red triangle meaning assertions are failing. 1 2 3 4 5 6 7 8 and 9, so 9 are failing. Similarly, if you cross check pass assertion, you'll find there are 11 pass count in this waveform. Okay, so this is what you can understand $change system function. Similar to this, there are some other system functions are available. Let's try to understand those also. So this $count once system function is there. This system function returns a count that represents the number of bits in the expression set to 1, meaning it returns the number of ones in while. Let's say if we are writing at every passage of the clock $count in while, it will return the number of ones in this while signal or variable. And if there are unknown or z, those will get signaled by this $counts system function. Similar to that is unknown system function is there. But this system function is unknown, returns true if any bit of the expression is unknown or z. If any bit is 1 or 0, those will be ignored by this unknown system function. Then $1 system function is there. This system function returns the system function basically returns the true if 1 and only 1 bit of the expression is high. So it is like $1 encoding FSM is there. You can verify with the help of this $1 system function. So if there is only 1 bit high at a time, it will return true, something like that. Okay. So this system function returns true or 1 if 1 and only 1 bit of the expression is high. The next one is $100. This system function returns true or 1 if at most 1 bit of expression is high, or you can say all the bits are 0 in an expression. Okay, so this is all all about the concept of system functions with respect to system Verilog assertion. Okay, so these are the basics built-in system functions that generally we are using in our assertion. So in the next video, we'll try to explore more about the other system functions too, like $pass, and we'll try to explore the advanced concepts of system Verilog assertion like implication operators, overlapping, non-overlapping, and so on with the help of practical exam. I'll put a link of this code in the description. You can go through the code, you can play around the code. Okay. So with this, I hope you have understood the concept of built-in system function and system Verilog assertion. And also I hope you enjoyed this video. So thanks for watching this video. Thank you.